Have you ever looked at a bridge spanning a saltwater bay, or maybe a car that's been driven through harsh, snowy winters, and wondered how the steel underneath doesn't just instantly rust away? Well, the answer is literally all around us. Invisible, microscopic shields, some of them just a few atoms thick. We're talking specifically about zinc-nickel electroplated coatings. But creating a truly flawless shield isn't as simple as just dipping a piece of metal into a bath. It requires a perfect microscopic dance of organic additives. Welcome to this explainer. Today, our mission is to decode a really fascinating study that evaluates 4 microscopic additives to find out exactly how they help craft the perfect, impenetrable metal shield.
So, here's our roadmap for this explainer. First up, we'll define the perfect metal coating. Then, we'll meet our 4 molecular candidates. Third, we're taking things to the quantum level to test their reactivity. After that, we'll test their physical sticking power. And finally, we'll see exactly how the whole thing comes together in the final application. All right, let's jump right into Section 1, the perfect metal coating and the secret to anti-rust. Now, on a macro level, the big enemy we're trying to defeat here is corrosion, right? We absolutely need flawless zinc-nickel alloy coatings to protect steel. And doing this efficiently usually happens in a highly conductive chloride electrolyte bath. Now, sure, zinc and nickel atoms are the bricks doing the heavy lifting for corrosion resistance, but think about it. You can't just throw bricks at a wall and expect a perfect smooth surface. You need architects. And that is exactly what these organic additives are. They act like tiny microscopic architects, regulating the exact alloy percentage, making the metal brighter, and tightly controlling crystal growth during electrodeposition, so you end up with a flawlessly smooth finish. Moving on to Section 2, meet the candidates. 4 model molecules, let's get to know the microscopic applicants vying for the job of the perfect plating agent.
Okay, let's meet the lineup. First up, we have saccharin, or SAC. Next is sodium citrate, which we'll just call SC. Then there's 2-butene-1,4-diol, let's go with BD for short. And finally, that long chain molecule down there is sodium dodecyl sulfate, or SDS. Now, what gives these molecules their unique superpowers are their heteroatoms. We're talking elements like sulfur, oxygen, and nitrogen, just scattered throughout their structures. And those specific atoms, they're going to dictate exactly how each molecule interacts with a raw, unprotected metal surface.
So, to figure out which of these guys is actually best suited for the job, researchers put them through 2 absolutely grueling computational tests. Test number 1 is density functional theory, or DFT for short. This calculates their static quantum reactivity, essentially how eager they are to trade electrons. Test number 2 is molecular dynamics, or MD. This one simulates their real-world physical sticking power over time on an iron surface suspended in a liquid bath. Let's see who survives the gauntlet. Let's dive right into that first test with Section 3, testing reactivity, the quantum level. Okay, to really grasp these DFT results, we need to understand one key concept first: the HOMO-LUMO gap. I want you to think of this gap as sort of a currency exchange rate for chemistry. HOMO is the highest occupied molecular orbital. Basically, where the molecule has electrons, it's totally ready to just give away. LUMO is the lowest unoccupied molecular orbital, where it actually has empty space to accept electrons. Here's the key. The smaller the energy gap between these two, the easier and faster the molecule can trade electrons with the metal surface. So, a small gap equals a highly reactive, super eager molecule. And what's really interesting here is we can actually visualize this exchange. Notice those bright yellow and blue molecular orbital clouds? They show us the exact areas where these molecules are totally primed for attack. The visuals on the left show the HOMO clouds, highlighting the electron-rich zones just ready for an electrophilic or giving attack. And on the right, we've got the LUMO clouds, highlighting the electron-deficient areas just waiting for a nucleophilic or taking attack. By mapping out these clouds, researchers know exactly which part of the molecule is going to physically touch the metal first. So, when they finally ran the numbers, which molecule was the most eager? Well, one specific number really stood out: 2.9711. That right there is the maximum charge transfer capacity of sodium citrate, or SC. SC also happens to boast the absolutely smallest HOMO-LUMO gap of the whole group. This incredibly high capacity to just hand over electrons makes SC our most eager reactive candidate in a quantum environment, hands down. All right, so to sum up the quantum test, let's look at the reactivity power rankings. Sodium citrate easily takes the gold for eagerness. Saccharin and BD, they're sitting comfortably in the middle. But look down at the bottom. SDS finishes dead last. It's got the highest energy gap and the lowest charge transfer capability. So, based strictly on this quantum test, STS looks like a pretty terrible candidate, right? Well, hold that thought, because this next test changes absolutely everything.
That brings us to Section 4, Sticking Power, Molecular Dynamics. Because, being eager to react chemically is great and all, but these additives are operating in a dynamic, swirling liquid bath. They actually have to physically stick the landing on a solid iron surface and hold on for dear life. And these models brilliantly illustrate that exact process. We're looking at the physical reality of how these molecules anchor themselves in watery solutions. If you look closely at SDS, that long-chain molecule over on the left, you'll see it actually forms this highly organized layer completely parallel to the metal surface. Its hydrophobic chains align just perfectly. The visuals are super cool, but the hard data here is just staggering. Take a close look at the interaction energies. Remember how SDS totally failed the quantum reactivity test? Well, despite that, it generates massive interaction energies. We're talking up to a remarkable negative 416.129 kilocalories per mole at 40 degrees Celsius. Now, in this context, a more negative number means a stronger, more spontaneous anchoring. So SDS actually possesses unparalleled surface affinity. It might not be eager to trade electrons, but it acts like heavy-duty molecular glue, modifying the local interface to favor incredibly smooth deposit formations. But wait, there's another hidden metric in this physical test: deformation energy. Basically, this is the energy cost a molecule has to pay to change its shape when it actually sticks to the metal. And BAM is the absolute star here. It requires a remarkably low deformation energy of just 3.14 kilocalories per mole. What does that mean for us? It means BAM settles into place compactly and cleanly, without twisting itself apart. This makes BAM the perfect stabilizing agent, giving a stable adsorption that helps level out the metal surface without any of that chaotic crystal grain growth. Okay, we've seen the data. Let's move into Section 5, the final application, building the shield. It's time to answer the so what. How does all this highly complex computational data actually translate into a pristine, rust-proof metal coating on your car? Well, the huge reveal of this study is that there actually isn't a single winner. You don't just want one additive, you want a sort of Avenger-style team, where every single molecule plays a highly specific role based on its own unique strengths. SC, our quantum winner, acts as the complexing agent. It stays mostly in the bath, managing the availability of metal ions. SDS, our physical powerhouse, is the surfactant anchor. It lays down parallel to the surface to create a smooth runway. SAC, as the green refiner, it strongly absorbs to stop chaotic crystal growth. And BD, it's the compact leveler, cleanly settling into microscopic bumps to guarantee a perfectly even finish. The researchers actually brilliantly summarized the big takeaway here. They noted that the combined results establish a clear structure-reactivity-adsorption relationship and provide a mechanistic ranking. Translated into plain English, by understanding these molecules at both the quantum and dynamic levels, engineers aren't just taking shots in the dark anymore. They can literally map specific functional groups to surface interactions and purposefully formulate the absolute perfect chemical team to build smoother, far more protective alloy coatings right from the bottom up. It really is just incredible when you stop and think about it. We are computationally designing the armor of our modern world, literally one atom at a time. Which leaves us with a pretty fascinating thought to end on today. If we can engineer flawless, rust-proof metal shields molecule by molecule today, using quantum theory and physical simulations, what kind of incredible invisible materials will these computational matchups help us build tomorrow? Thanks so much for joining me for this explainer. Keep learning and keep looking closer at the invisible world all around you.